Good afternoon, everyone. So after having two sessions about mathematics of learning systems, now we are ready to invite our first invited speaker, Dr. Manjesh Kumar Hanwal. He's going to talk about online learning and bandit algorithms. He received his BTech degree in ECE from NIT Bhopal and MS degree in ECE from IISc Bangalore and PhD from Indria, France in 2013. After 2 years of postdoc at Boston University, he joined IOR department at IIT Bombay, where he is an associate professor now. His research interests include communication network, machine learning, and cyber security. He is recipient of Inspire Faculty Award from DST, earlier career research award from SERB, and he has also received several research grants from Government of India and CEFIPRA. Okay, so without further ado, welcome Dr. Manjesh.
And I also thank the organizers for inviting me here to talk, and thanks Naveen also for asking me to come and give a talk here. So I'll be talking on this online setup. Online learning is a very big area, and if you just search online machine learning, you'll see several topics, and in that I'm going to particularly focus on bandit algorithms. So I just want to understand the composition here. I mean, can I just ask how many of you are already heard about bandit algorithms here? Especially, I mean, non-faculty members, the other audience. Okay, fine. So what I will do in that, like, I'm put my talk in two parts. The first part is on the basic introduction to bandit algorithms. And the second part, I wanted to talk about one of the work we did on bandit algorithm, which extended some of the results that are known in this bandit algorithm. But what I will do is, now it is about 4 o'clock. For about 40 minutes, I will cover this basics of bandits, and maybe like with after a short 5 minutes break, in the remaining 30 minutes, I will talk about the work we have contributed to this area. Okay, just a quick promotion about our group. Like, I come from this IOR department. In that we have this Millions lab. This Millions stands for Machine Learning in Operations, Networks and Security. So basically we apply machine learning to these three domains: network, operations and security domain. And there is also one center that I am looking after called Technocraft Center for Applied Artificial Intelligence, where we are doing various industry related projects that requires machine learning. Okay. Yeah. Okay, now what is about this online decision making? Like, we know that, right? Like, just think of some salesperson and you are into selling car business. So a new product has been launched. You don't know a priori how the demand for that it will be. Then, like, let's say you are a dealer and you have to choose one of this for selling it. And obviously, as a dealer, you would be interested in selling more number of them, right? More number you sell, more profit you are going to make. Then the question is, as people buy your car, so then is it possible for you to decide, as you keep on selling, which one of these items that you want to stock more so that you can sell it more? So here the thing is, you have to do it in an online fashion. A priori you don't know the demand. You are going to learn and you are going to know which of them is more preferred by the customers, and accordingly you are going to stock them and sell them. And the second one, the more classical example, is the vaccine trials. And in fact, most of the this bandit literature that was developed in the early 1930s was based on this vaccine applications. So what is here? We have gone through all this, right? In this recent phase, many drugs have come into the market, but before the drugs come into the market, it has to go to user trials. And you can't do user trials, like you can't say, okay, come 1,000 people, I will test on you, and after that I will decide. I mean, human life is at stake here. So what you have to do is, you have to use minimal number of people and from that quickly identify which is the best, most effective drug, and also discard the ones which are harmful. So all these people, before they come up, what they would have done is collected many volunteers, tested these drugs one by one and see how they respond to them, and based on that they would have adjusted the composition of their drug so that it becomes most effective. So there also, like, you give the drug, see how the response is, and accordingly you change the composition to come up with the best possible drug. So there is like a kind of online updations you are going to do here. Okay, I think some figures got jumbled here, but this is the basic. These were the motivations, like drug trial, based on which this online setup came, this banded learning setup came. But now it's so generic that people have started using it in various network scenarios also. Like for example, in the packet routing, like you have multiple packets to routes to transmit your packet, but you don't know the congestion level on each one of them. Which path you are going to choose so that it's most effective. So you are going to send your packets through different routes, see what is the latency, and based on that maybe possibly you will identify the best one. And similarly, if you look into online recommendation over the internet, this is also where this online learning or the banded setup has been widely used now. Like suppose you have bunch of actions, ads to put, and when you as a web page designer, you want to put an ad which will be liked by more people, because if you click on an ad, that is money for someone. So they want to put an ad in a web page that is mostly clicked by, but a priori they don't know what is that you are going to like. So they will put something, if you click or not, based on that they will update which ad is going to be liked or preferred by most of them, and then they start showing better one. So their goal is to make sure that the clicks are higher. Okay, and here the learning is also happening in an online fashion. And now talking about wireless setting, and this is our mostly interest, like we want to eventually take as electrical engineering background, we want to see that how all the things we learn in this online setup can be leveraged in the wireless networks. I will talk about this more, but just to give you a crux, like there are in the modern day, like you have picocells, microcells, and there is so much of interference going on. So you don't know which channels to use. Like obviously you want to use a channel which has less interference so that you get a better rates there, but you don't know what kind of interference is coming to me, and you have to basically figure out learning. And this is where another thing, like how to use this online setup or the bandit setup so you get maximum throughput in your network. Okay, now we see a couple of applications where online interaction happens, and there are various domains in which these interactions can be leveraged to do something better. So now what we'll start doing is, let's start thinking them in an abstract way. Okay, so if we, instead of thinking into a particular application, let's see how to model this online learning setup itself, and see if we can set up some criteria for evaluating our methods. Okay, now in crux, what we can think of, we are basically dealing with an uncertain environment, and we have to make decision under uncertainty. Okay, so the environment I don't know, but the good thing is I can interact with this and try to figure out what is best. So let's say you have bunch of actions to take. I mean, in the ad placement I told, like these could be the bunch of ads that you want to select. In the wireless network, this could be the bunch of channels you need to select. In the routing problem, this could be the bunch of routes you have to select to transmit your powers. And each of these actions have certain mean rewards associated with them, which a priori you don't know, because you are dealing with an uncertain environment, you don't know them, and you have to figure out them by interacting with your environment. Now what you can do is, fine, you don't know anything, maybe initially you start taking some actions, but you are going to make observation whether your action was good or not, and what you are going to get is random rewards here, because this is an stochastic, the environment could be stochastic here. And now in this question, like, you want to basically try to select an action here which does on an average best, which is on an average best for you. Now the question is how to figure this out, how to figure out by interacting with environment which action is the best for. Okay, now I want to like take a moment and try to distinguish what I'm talking this online learning and what is this batch, the batch learning that we have been seeing. I think I'm sure most of you might have heard about supervised learning, unsupervised learning, or active learning, or semi-supervised learning, right? What's the difference between this online learning and all these other methods? So I have put all the methods, going to call it as batch setting. Why? Here you have a bunch of data already given to you, okay, and you have been asked to find a one good classifier from the bunch, or like you have been given a bunch of hypotheses and asked to find a one good hypothesis on that. And now what you are going to do is, for example, if I take a simple binary classifiers, a binary classification job, you have to ask to identify one hypothesis which best classifies this given data here. And you will come up with your own method, define some loss function, and from this you will identify one of them is good. But once you do that, what we call it as a training part, then what you do is, okay, fine, you discard whatever you have. Now whatever you found one, you are now going to use on the rest of the, you start using it in your rest of deployment. Whatever comes you use to classify the new examples. But in an online learning, we don't have the luxury of collecting, we don't have the luxury of having the availability of all this data before we start making decision. We don't have the luxury to learn offline and then go for deployment. In online, from around day one we are in the deployment stage, and we make something comes, we have to make a decision. Right now I don't know it's good or bad. I make a decision, I receive a feedback, and from that I have to improve my decision. So there is a continuous learning happening here, okay. So that is what online learning is basically, like you are continuously learning and improving what is the best you can do, okay. So again, one more thing is, like, I'm just again trying to contrast with what we are going to do in the online setting. I am putting again this batch setting. So what is the classical batch setting? You will have a set of features and you have a set of labels, and there is some labeling function which could be latent, you don't know, and you want to find the best hypothesis from a set. All this, I mean, here x is known, y is known, h is known, f is not known to you. You want to somewhat figure out what is that f. Now to do that, what you will do is you assume that you have a data points, like this m data points are there, such that for ith data point label is f of xi, okay. And now these xi's are drawn from some distributions which you don't know. Now how you are going to solve this problem? You are going to basically set your criteria as minimize your expected loss, and you come up with your own loss function when that is subjected to like your requirements. Now once you know the loss function, the simplest thing is to do is go with your empirical minimization, and once you do this empirical minimization, whatever that argmin here, you take that and use it in the subsequent rounds. This is the classical one. But now we can't do this right away because all the samples are not readily available to me. Maybe in the first round, first sample is available, but I have to make a decision. After I make a decision, I have to see whether I have to improve my decision, and I again make a decision, and then I see the second point like that. So only one is revealed to me, and at every point I make a decision. And here I am going to talk about the classical and the simplest bandit setting. So we are going to the number of actions we are available, we are going to call them as arms. Let's say if you have k actions to deal with, let's call them k arms. And this arms notion is coming here because of this canonical bandit setting, where you can imagine that you are trying to find out which is the, if you go to a casino and you don't know which machine you are going to win, but you are trying to find a machine in which your winning chances are the highest. Like that. So here you can think like you are pulling some arms in a slot machine in a casino, like that. Okay, now coming back here, yeah, you have k arms, and what you are going to do is the interaction happens iteratively. Like you play with one machine, you observe what happens. Maybe after that you will go to another machine, you play, and you are going to observe what happens. So interaction happens like in rounds t to 1, 2, 3, and after each play you are going to observe some reward after you play. So this is the interaction, like this is your environment, you play an action and you observe the reward, and using that observed reward as feedback, maybe you are going to decide what is the next action. Now what is that? The policy is now here is going to be what is your action selection strategy. At each round t, you have to decide what is the action you want to take. You take it and then you observe something, and based on that you decide in the next round what is the action you want to take. Okay, okay, now we know this setup. Now just to make it little mathematically formal, we need some setting and also some assumptions to say like what is that policy we have, and how is its performance to evaluate. We need some formal setup, and that is what we are going to do now. And now I am going to look into the one specific case called stochastic multi-arm bandits. So multi-arm bandits are in various flavors, and one of them is stochastic multi-arm bandits. And in this case of stochastic multi-arm bandits, what we are going to do is we assume that whenever you play an arm, that arm is going to give you a reward which is drawn from some underlying distribution. That distribution I am going to denote it as nu I. Okay. So in the classical the batch setting, what we assume, the data is coming from certain distribution, right? Analogously, we are assuming each action is going to give me a reward according to some underlying distribution. Okay. And we are going to assume that the arm rewards are independent. Like if I have k arms, each has certain distribution and these distributions are independent. And also every time I play an arm, its reward is independent. That is this IID. I hope you already know what is an IID, like the rewards are independently drawn. And each arm is going to associated with a mean, which I am denoting it as mu I. That is the mean value of the reward that I am going to give me. And this we already saw, like whatever arm you are going to select in round t, that I am going to denote it as IT. And if you are going to play arm IT, this is the reward you are going to observe. So this is how the interaction happens between. So we can think this online learning as a game between environment and a learner, or game or interaction, whatever you call it. So environment is going to generate rewards according to the underlying distribution, and the player is going to select an action as per his own policy based on his past observation. And once he plays, he is going to observe a reward according to the action that he has played. Okay, this is the, so environment is basically has generating the rewards, and player selects an arm and he sees the reward associated with that. And depending on the feedback, again one can think of lot of variants here, and that's what I wanted to highlight this point. What is this feedback? And this feedback could be of different nature. One thing is what we call it as a full information, another is what we call it as a bandit setting. And what could be the full information setting? Full information setting is like you play one arm, anyway by playing that arm you know what is the reward that arm gives, but if you also get to see what other arms would have given, that is like a full information. Okay, so in one round you basically saw what all the arms would have given you. For example, in the casino thing, right? Or maybe like I have another example. Okay, in the stock market, let's say you are a stock market enthusiast and you do a lot of investments. What's going to happen? Like you have option to put money in certain stocks, right? And each stock, whether it is going to give you returns or not, that is like you don't know a priori. It depends on so many market conditions, right, which is not in your control. Now, if you put money in certain stock, at the end of the day, you know whether that stock went up or not. And if it went up, you made money. If it went down, you lost money. But the stocks in which you did not put money, you also know how they did, whether they went up or went down. Even though you are not losing money or gaining money, you have not put money there, at least you got the information about this. That's like a full information. Like you got to know about all the, what would all the actions would have given to you. On the other hand, the bandit setting is you only get to see the feedback about the action you took or the arm you play, and not about the other actions which you did not play. And yeah, example here is a drug test, right? Like if you have certain drugs and you give one drug to a patient, you only get to see the response of that patient on this drug. Like other drugs you did not apply, you don't know what happened to that. So here whatever the action you take, you only are observing reward for that. So mostly we are be following this bandit setting here, okay? And actually full information thing is slightly easier compared to the bandit setting. So obviously, which setting has lesser information here, full information setting or bandit setting? Bandit setting has less information. If you have less information, that's a more difficult problem, right? Because my learning becomes complicated. Performance, like how you are going to evaluate performance, maximize the accepted reward. Like if you are going to run T rounds, this is the total reward you are going to get, and you want to see at every time, like this should have been T1 to T rounds, right? You want to pull the sequence of actions such that this reward is maximized. The expected reward. I am talking about the expected reward here. So now I want to select my IT in each round T such that this is maximized. And how I can select IT? If I have to select IT in that round, I have this much of information. So let's say in round 1, I1 is my action, and you observed X1 I1 associated, and in round 2 I took I2 and this is the associated. Until round T minus 1 you have this much observation, and based on this you want to select what is your IT. What is the best one could get here? Suppose let's say that I star is the one which is giving me the maximum mean. Okay. Now obviously the optimal thing to do here is, like if you are a oracle, okay, I told you a priori these are the means of the action. What you would have done? You would have simply computed the arm which just gives me the highest mean, and you play that in every round, right? That is your best policy, right? You don't want to do anything else. If I tell you that, okay, I mean in the stock market example, right? Like these are the 5 stocks, and I already told that this stock is going to give you 30% return, this guy is going to give you 20%, like that, and their behavior is the same throughout, then obviously you always put money in the one which is going to give you the highest return all the time. And that is your I star, and you are going to do that. You play I star in every round, and the total reward you would have got in is simply T times mu I star. In each round you are getting in expectation mu I star, and this is your total reward. Now I am not oracle, nobody has told me what is this mu values a priori, and I have to figure them out, right? So what I am going to now do is, whatever my policy, I am going to compare the reward I get against this Oracle policy. So Oracle is a benchmark for me now. I want to do as good as Oracle, and I want to see how close I can come. So for that we define this regret. So regret is basically, this is the Oracle would have gotten, and this is what I get. The difference between this is going to be called, we are going to call it as regret. And I mean, this is some simple mathematical manipulation I have done, and you can write it as, because this expectation, this you can pull it, right, this is the expectation of that arm, and if you do some manipulation you can express this in terms of this regret, where NIT is how many times you are going to play the ith arm times what is the gap, optimality gap. So what is delta I here? Delta I is the difference between the mean of the optimal arm and that, so this should have been mu I here, that is mu I star minus the mu I. So this regret in writing this is obvious, right? Like you basically counting that, okay, how many times each of the arms you have played, and that was how much of deviation it was giving me with respect to the Oracle reward, and you are basically summing all of them. This is my regret I have defined like that. Suppose if I divide this regret by t and this goes to 0, I am going to call it as consistent policy. But now let us try to understand what does this mean. RT by t is going to 0. What does this mean? Regret per round is going to 0 as t is becoming large. Does this mean like on an average I am doing as good as Oracle as t tends to infinity? Yes or no? Anybody feels it's no? So basically RT by t going to 0 means what? This ratio has become smaller and smaller, right? That means that this should be also, this gap is not much. Okay? So this can go 0 only if this t is becoming larger and this RT kind of saturates. So this is what, like if RT by t goes to 0, that in a way means on an average I am doing as good as Oracle, but only when t is going to infinity. I am letting t goes to infinity because when I am learning I can't expect to start doing as good as Oracle in the initial rounds, right? I need certain time to learn, and after learning I want this to go 0. Only thing this is ensuring is, right, my learning should not take too much time. It should happen quickly so that this numerator saturates and the denominator kills it as t goes to infinity. Now the question comes, okay fine, how to achieve this? How to achieve? Is it possible to even achieve this? What is this consistent policies? As you see, there are two parts here, right? One is I have to somehow learn. Once I learn, I have to start playing the best one. Then only regret per round can go to 0. So this brings us to something called exploration versus exploitation trade-off. Like I need to learn quickly and also start playing the best one more frequently. Now the question is, how to do this exploration and exploitation trade-off? Like there has to be fine balance between. So basically, what is exploration? Like you are trying to explore the arm and trying to figure out which is the best, and exploitation is like once you identify, you keep on playing it and trying to accumulate as much of a reward. So let's talk about some basic policies. One is simply called random selection. Like you have t rounds and you have k arms. You assign equal number of rounds to all of them, t by k, and play each one of them. So what you have done is basically explored each arm equally. Is this a good policy?
No, sir.
Why?
Some arms have more.
Yeah. Some arms could have better one, but you are treating all of them equally, right? It's not a good choice, like, yeah. So let's choose the second one, like choose the empirically best arm in each round. Empirically best, I hope you understand what I mean by empirically best, right? Like you play certain arms and you see, okay, so far who gave me the best one, and start playing that guy the next round. Like you are trying to be a little bit greedy here. So far what has done worked best for me, I want to do it in next also. Does this going to do better for you? It may not actually, because things can be deceiving, right? I mean, some bad thing is started doing something better initially, but later it comes to start showing its true colors. So then you should not do that. You may get stuck. Basically, if you use this, you may get stuck in a bad situation. Other option is you kind of decide you have T rounds. Only initial few rounds you kind of explore fraction of the initial rounds, and after that you exploit. What do you think? This should be better than the previous two? Possibly, right? But then tell me what is epsilon. Epsilon can be anything between 0 and 1, right? Like if you are going to put epsilon to 1, right, this is more tending towards the first policy. You are just exploring all of them. And if you put epsilon equals to 0, maybe you are tending more towards the second one. But I have to balance them, like I can't be extreme. That is the whole question, what should be the right epsilon? Okay, so that's what, like too much exploration or premature exploitations are both bad. I have to find a balance between them. So this is one toy example I have just put. Like I have just shown you, like I have taken 5 arms with certain means, and for different values of epsilon, I have put what is the reward you get. You see that when I have epsilon 0, I got this much of reward, and this is the oracle policy. Oracle has this much and I got so less. And I am increasing epsilon here, but you see that like, yeah, it has increased, but it's not always that like increasing epsilon. So there is, you see that there is some sweet spot here, which a priori I don't know. So this is just like saying that, yeah, some exploration and exploitation has to be properly balanced, and that actually could depend on all your problem parameters, which you don't know a priori. The mean values you don't know a priori. Now we have to learn this, and yeah, now the good policy has to do this balance well, and for this people have proposed many policies, and I am going to quickly take you through these 3 important policies called UCB1, KLUCB, and Thompson sampling. Okay. So before we get into these policies, let's try to understand what is the best we can do. Okay, is there any fundamental limitations here what we can do, or like we can always go and do whatever oracle does? Okay, so for that there is a lower bound in bandit literature. I forgot to put the references here, but this is something called a famous Lie-Robin lower bound. What they said is, whatever your policy, if it is consistent, it has to have some lower bound. Okay, and there is a constant rate at which this, if you took into the ratio RT by log T, I mean it has to be limited, and it has to be lower bounded. Okay, so if you don't understand at this point, leave it, but just saying that it is kind of giving what one should expect when you are trying to develop a policy. Okay, so there is not like you can't do any arbitrary thing. There is some limitation on what you can do, and this result is saying that, yeah, I mean this RT will be growing at certain rate. Roughly it says that RT is going to grow at rate log T, order log T. Like if you are going to run more rounds T, your regret is also going to be more. It's not that your regret will be 0 after some point. It is going to grow more, and that's what it is trying to say here. It is because there has to be continuous exploration. In this thing, you can't stop exploring. At no point you can say that, oh, I have learned everything, now I don't need to explore anything. I am going to only play this how. If you do that, there is a chance that you have made a bad choice. So in life also, always explore. I mean, don't say that enough explore and get stuck to something. So explore, maybe you will find something better. And it depends on some information carrying quantity called KL divergence. I hope all of you know this Keval divergence, right? Now the question is how to achieve this optimal consistent policies, and that is where all these three algorithms come into picture. Algorithms based on optimism will do is, based on whatever you observed so far, they try to build a confidence interval around that. So all of you understand what's confidence interval? Okay, if not, like it is just like, let's say, just think about this. Let's say you have 4 arms, and I have this big diamonds actually represents, the middle ones represents the mean of the arm, and around this you can construct, you may not, after certain rounds, you may not know exactly this is the value, but you can be confident that my mean value will be somewhere in this range. You kind of say that, okay, I'm not sure I'm exactly here, but I'm sure, I'm more or less confident that I'm somewhere in this much close to it. Okay, so that is what this confidence intervals tell, and confidence intervals you can always have the lower value, that is like what is the lower value I have, and also the upper value. So the lower and upper value will give the confidence intervals and also the confidence length. So at any point you can build this confidence interval, and what this algorithm is saying is, anyway we are facing with an uncertain environment, you don't know what has been done so far is good or bad, but at the current moment pretend that everything is good, and whatever you have based on confidence interval, take that as the true value and go with whatever the best you have. Let's say these are the upper confidence value. You don't know this could be the right value, all you know is your value is lying in this, it could be this also, right? But just pretend that this is the actual value, and like that you take the values, the upper confidence value for each of the arm, and go with the one which is giving you the best value of that upper confidence one. Okay, so this is what you are saying, like if you are faced an uncertainty, you are going to only have this, you are have things only to some confidence, and go with that confidence itself, go with your whatever the confidence you have, go optimistically on that, and try to select the best one. Okay, so this is what is called as optimism principle, and this algorithm itself is called as UCB algorithm, and you see why the UCB, right? It is based on upper confidence bound. What is the upper confidence bound, right? Now these intervals also you can construct in various ways. Okay, I mean there is a rich literature in probability and statistics. People have written multiple theses on this and done their lifetime research on this, like how to come up with these upper confidence bounds. One possible way is define it in this fashion, where the first part is the simple empirical mean, and the second part is actually comes from the confidence term, which we call it as exploration bonus. So here you can see that, okay, let's spend a minute on this. Here nk is the number of times you have played that arm, and t is the round in which you are now. So you see that if you play more number of arms, this guy is going to shrink, become smaller. That means you are basically, because more sample means your confidence intervals are shrinking, because you have observed it many times and you are more and more confident about it. So your interval can be. On the other hand, if you have played it long time but not have many samples, you may not have many confidence, and that will force this log t will be increasing, right? So it will ask you to watch it more again, because you have observed others too many times but not this one, so it will ask also like make its UCB more and ask you to play that arm. Okay, fine. So this is the basic idea, like in the UCB you are going to upper confidence, you are going to construct, which will have these two parts. This is exploration term, which is coming from your confidence term, and this is your exploitation term, and it is taking the sum of these two. And if you are going to do this, there is some nice analysis you can do using Hoeffding's inequality and some finite time analysis that is used to to analyze such things. One can show that the regret, you can bound it like this, which is actually order k log t. Now, if I have order k log t, can I say that this algorithm is consistent with the definition I said earlier, right? What was the consistent definition? RT by T should go to, is it going here? Yes, right, because RT, now this is log T here, if you divide it by T, log T by T will go to 0. So, this algorithm is consistent. That means asymptotically it is doing as good as a oracle. Yeah, here delta, this delta here is something called suboptimality cap, and that is coming in the denominator, and this is natural that if the suboptimality gap is smaller, your complexity is more, and this captures this. Okay, one point I want to highlight here is that all this analysis is assuming that your rewards are somehow in the some support 0 1. That is assuming that your mean values or rewards are giving in the interval 0 1 or in some bounded one. Okay, now I have some basic probability question. If your support is bounded, let us say between 0 1, what you can say about its variance? Can its variance be more than 1 or it has to be less than 1? Okay, simpler question than that. What would be its mean? The mean will be between 0 1 or it will be more than 0 1? It has to be 0. What about variance? It will be between, it has to be between 0 1 itself, right? So, now this is kind of assuming that your support is bounded, which automatically implying that your variance is bounded, right? I will come to this point later when I will say that how this could be overcome, okay? Because in always we will not be always working with uniform distributions, right? You may be working with Gaussian distribution. Gaussian has what? Unbounded support. Okay, so on that case, this kind of results may not hold. So this is another algorithm. Like as I said, the confidence term, the exploration bonus is very important. People have come up with different confidence bonus, and another term is called something called KLUCB based. And here you are going to define your UCB based in this fashion, like you are going to check whether your divergence has exceeded some quantity or not. I mean, this is just like an algorithm, like here you are going to again find the maximum value, but here the term you are going to use is something called right upper confidence bound, that is again coming from some different analysis. I am just putting here, we do not need to get into that. And that is why, because this KL divergence is involved, it is called KLUCB. And actually for Bernoulli distribution, if you look into its distribution, actually one can show that it is getting regret, which is delta by D, which if you recall does something strikes if you look into this and what I said earlier with respect to lower bound. Actually I am getting that as also upper bound asymptotically. That is whatever best I am getting it here for specific case of Bernoulli banded distribution. So that is what that KLUCB is asymptotically optimal. Okay, just I want to spend 1 minute on this and we will stop here. So there is another approach. What we just saw is that UCB and KLUCB, right? You find empirical means, right? So when you find empirical means, it is basically frequentist analysis. You basically counting how many times I have observed this, and based on that you compute the empirical means. But there is another approach called Bayesian approach. In the Bayesian approach, like it also, instead of saying that your parameters are fixed, though unknown, you are going to assume that these parameters are themselves coming from some distributions. You are going to put some Bayesian prior on that. Okay? So because of that, what you will do is you will have prior probabilities and posterior probabilities, and as you observe more and more samples, you improve your posteriors, and based on that you make a decision. So This is based on beta distribution. How many of you heard about beta distribution? Beta distribution, okay. Beta distribution is just like a more generalized version of uniform distribution. If you don't know, don't worry about it. It just like looks like this. Uniform is like a flat, right? Uniform is like flat over 0, 1. But you can generalize it and maybe put more mass on some region and you can get a beta distribution. So it will be depending on the success and failure, it depends, updates its posterior and try to find an optimal. So just think of this figure, like you have these different arms and on everybody you are trying to put a, let's say, Gaussian or beta. Ideally what you want this distribution to focus more on the means. That means when you are going to sample from this, you are going to get a sample very close to that. So it is just based on that idea, and what it is doing is, this mean values, it tries to draw from this posterior distribution that becomes like an index now, and it is going to choose the one which has the highest index. So those who are interested, take a closer look into this one. This is what is called as the Thompson sampling. What it does is, from the posterior, this pi a's, they are drawn from the posterior distribution you get and find the action which has the highest value of this value. So this thetas are sampled from the posterior distributions. Okay. So instead of just assigning index based on this empirical mean, you are going to draw those values from a distribution and try to find the maximum value of that. And this is called Thompson sampling because of this is in fact the first bandit algorithm that came in 1933, and this strategy was used in the drug trials. Okay. Okay. Okay, maybe I will just stop here now. So just notice that what I have just said is a very, very basic structure. Right now, this can be used in many different applications, and people have come up with so many different variants of this, like depending dueling bandit, model bandit, chip bandits, Rotan bandits. I mean, depending on the different applications. If you just search on the internet bandit, you will see all of that. And this is still a very active research area. People are not only looking at application, but also trying to richly improve this literature itself. Like they look into, earlier I say arms are independent of each other, fine, but maybe there could be some structure. Maybe arms are like means are increasing or maybe decreasing, increasing and decreasing. Maybe they will have some unimodality structure, maybe they will have smoothness structure. How to use that structure, any additional information you have, how to use that structure. Okay, with this I'll stop here, and there is another adversarial bandit. Maybe this is, I'll put these slides if you are interested, take a look into that. Because of lack of time we will not get into this.
Any questions to this?
Yeah, if you have any questions, meanwhile, yes. Anything like about this application, not necessarily what we just discussed, their applications and all.
So are there algorithms which will take both temporal aspects and the distribution of different bandits in 2 dimensions and try to do something? Different arms we have, and then each arm will be giving its
Samples.
samples
Yeah.
over time
Yeah.
when we make different experiments.
Ah.
So if we consider this as a one on the
Time series.
axis,
Ah.
and other on the spatial, the other different arms. So if
Right.
we put them in two
Yeah.
dimensions, roughly if we get a 2-dimensional distribution,
Yeah.
getting a peak of that 2-dimensional distribution, will that help? Is there any?
See, like what in this our assumption is both in time and space, these are IID samples. That is what we said, right? Like across the time also they are independent samples, and if you look into different arms, they are also independent. because of that, like, yeah, we will not get like the peak information will not help. Yeah, because we need to look into the average. Yeah. Yeah.
Suppose you want to simulate, generally what we do is we fix the mean of the arms, arbitrary,
Yeah.
so it's there.
Yeah.
But here you just assume that it's coming from uniform distribution,
Yeah.
right?
We are not
It
assuming.
could be, what should be the best choice for the initial distribution?
The best choice is like a beta, because the good thing about beta is posterior and prior both are beta.
Yeah, okay,
Yeah, and because of this updation strategy becomes very simpler.
right.
Like if you assume that initially they are beta distribution, after you observe one set of samples, the posterior is also beta distribution.
Right, okay.
I think that is the reason people use beta
Okay,
distribution.
fine.
Yeah, of course, like you can come up with your own different possible distribution, but that makes analysis harder. Say that again? Yeah, Gaussian also you can use, yes. But support is an issue, and also like sometimes you may have discrete samples, like Gaussian means continuous, right? So yeah, depending on your application, discrete or continuous, yes, Gaussian is also been used, like, and beta is another option when you have discrete values only. Yeah.
So are there works which model as HMMs are state space kind of modeling? Say along the temporal aspect mainly.
Okay.
So if we consider each is the next state that evolves.
Okay, like I mean, you want to model this as like a state, right? You want to bring in some Markonian structure here.
Correct.
Yeah, I think that Gitin index is all look into such Markonian structure. Yeah. I mean, I not followed much, but I think there are literature on this. Yeah. People do consider some dependencies, Markovian, and even other, and yes, looked into it. Yeah. We talked about the very basic version of stochastic multi-arm bandit. Okay. Suppose I tell you, when you play an arm, I will tell you something related to it. For example, okay, I will come to the examples, but the whole question is, if you have any additional information, should we incorporate or not? We should incorporate in learning, right? Because if you have any additional information, if you incorporate in the learning, maybe that will only help us learn things faster. We wanted to look into that aspect. If whatever the arms we pull, we anyway going to get the reward for that. But if there is something additional information we get about that arm, maybe we should use this. How to use that? And in this work, we try to understand and develop the theory for that. And that additional information you will see later, like we model it as a control variate, which is a very famous tool that has been actually used by statisticians to get a better estimates with a improved variance. I mean, these are more statistical terms, but yeah, this is what the control variate theory has been used, and we will see how we have exploited that. Yeah, this work is what like we presented in NeurIPS 2021 last year, and this work is with my PhD students called Arun Verma, who just graduated last year, and he is now a postdoc at NUS Singapore. Okay, a quick recap of what we talked about this stochastic bandits. We said that there is one learner and there are these k actions, right? We set our goal as maximize the sum of the rewards. This was our goal in our stochastic multi-arm bandits. And we said that there is a learner and there is an environment. Learner takes an action and he will observe the reward as a feedback from that. So this is the interaction that is going on between learner and the environment. And these rewards are drawn by some distribution. I think I just used a different notation. Earlier it was new, but we are writing it as a D1, D2 here. These are the distributions associated with the arms. And again, like we wanted in the classical one, there is the policy is going to whatever you have observed so far, based on that it is trying to find what is the next action that you are trying to use. And we try to measure the performance using this notion of regret, which we defined as whatever the best one can get that oracle would have obtained, knowing the full problem full a priori the mean values and what you would have gotten, the difference between that we defined as regret. And we said that we wanted to minimize regret. It is same as saying the okay, maximize your the sum of the accumulated rewards. Now again we said that good policy should have this sublinear regret, that is as t goes to infinity it should do as good as an oracle on an average. And we again saw this exploration versus exploitation things, and the main trick to get a better performance is to balance them, exploration and exploitation. And one algorithm we saw is UCB1, which was of this form, right, where the first term was the empirical mean and the second one was this exploration bonus which is coming from your confidence term. We took that. Now this was a classic result, UCB1, and they were able to come up with one nice this confidence term bound, based on which we are able to show that this UCB policy is have a sublinear regret. Now the whole trick of any algorithm is in terms of how you are going to choose your action in that round, and somehow if you are able to better control your exploration, maybe will be also able to do better. So just think of that let's say you are just to take a 2-arm case, one has a mean of let's say 0.1 and another has a mean of 0.9. So one arm is a very high reward and another is a low reward. And take another problem where one arm has a mean of 0.4 and another arm has a mean of 0.5. Okay, which one is difficult? Second one. Why not first?
It is clearly evident in the first one.
It's not evident, but it will soon become evident, right? Because one is giving so much high and another is. So here you don't need to do too much exploration, right? Maybe after a few sample itself you got. But on the other one where it is 0.4 and 0.5, things don't become evident soon. You need more samples, right? So somehow you need to better control exploration. If you can better control exploration, maybe you will quickly identify which arm is the better and you can exploit it. Okay. So now the whole trick seems to be lies in how to get this tighter UCB balance between explore and exploit, and if somehow you are able to construct a sharper confidence intervals, right, maybe you can reduce exploration quickly and focus more on the exploitation. So when I say you quickly come up with sharper confidence interval, maybe you need to have some better means to know that okay, with this many sample itself I will be more like you will somehow say that okay, within, instead of giving this much as the interval, you want to now give it something smaller. Okay, so that you know that now your arm is within this. Instead of, if you are going to give me this much, my mean is going to here, and if somebody gives me another one who says no, your mean is going to be in this, second one is better for me, right? Because that guy is giving me shorter interval over which my mean lines. Instead of getting a bigger interval, I would prefer somehow if somebody gives me with the same confidence shorter intervals. Okay. So somehow if you are able to get this better confidence with either a smaller one or like reduce the number of samples you need to get that much, then that is a better. And what we are now going to do is focus on that, like when we can do this. Is it possible to instead of getting this much big confidence interval, is it possible to get a smaller ones? Okay, so KL UCB compared to UCB, it has actually a tighter, smaller confidence interval, and that is what we saw that it is actually asymptotically better. Just because it is able to come up with a better confidence intervals, sharper ones. Other possibility of improving your things is use variance information. When is this useful? Like suppose I told earlier, right? I told you if you have a bounded support, your variance is also bounded. But now suppose you have unbounded support. Now, but it may have finite variance. Like take a Gaussian distribution, right? It has unbounded support, but it may have finite variance. Now suppose if we can use that variance information, maybe you will be also able to do better. And there are some algorithms actually it does that job, like UCB variance. Actually it incorporates the variance information in the UCB algorithm to better, and this EU is, did I correct this? This is EUCB's Professor Naveen's work. Like he has also incorporated this variance information to improve confidence intervals to get a better performance. If you have this bounded variance, this variance should somehow impact your regret performance, right? Maybe in the case of finite support, it did not come into picture the variance terms because the bound support was like between 0 1 and that maximum bound becomes your bound on variance also. So variance did not come explicitly. Maybe like when you have this unbounded support, maybe variance should explicitly come into picture. What we want to do is, if we have this additional information, what we are going to call it as control variate, how they can be used to get a better variance, which in turn will lead better performance of your algorithms. Okay. So now what I am going to do is I am trying to move away from the bounded support notion. Now I am not assuming that my support is bounded, my support can be unbounded. My variance is bounded though, like I can't assume my variance is unbounded. Now I want to see that how I can leverage any additional information I have to come up with a better variance in my estimator, or how I can incorporate this variant information in my algorithm. So before we discuss how I can incorporate any additional information, I want to quickly take you through something called control variate. Okay. So control variate, as I said, is a classical statistics method which was basically developed to control your variance. Rather, I would say like reduce your variance. Okay. Suppose let us say mu is some quantity that you want to estimate, and let us say you are interested in unbiased estimator, and let us call W be a random variable which is actually correlated with X. And I hope you understand what I mean by correlated. And now if it is correlated, and now we are going to treat anything that is correlated with X as a control variate of control variate. This should have been X, but this is a typo here. So any random variable W that is correlated with variable X of my interest, I am going to treat it as a control variate. Now X is my estimator. I mean, I am interested in, this could be random variable X and it could be an estimator, and it is being used to estimate a value parameter mu, and I am interested in unbiased estimator. Now let us say I am going to now change this X in this format. X, I have adding a linear term here, beta, and this is a control variate, and what is omega here? Omega is the mean value of this control variate. I have added it like this, and now this weighted sum, in this, if I am going to choose this beta as the ratio of the covariance between x and w and the variance of w in this fashion, now the variance of x bar is 1 minus rho square of variance of x. So now you see that, right? Now whatever is the variance of x, now if I compare it with the variance of x, now that is being multiplied by a factor of 1 minus rho square, and this rho is the correlation coefficient. And what is the range of correlation coefficient? Minus 1 to 1, right? So because of that, this quantity will be between 0 1, 1 minus rho square will be 0 1. So this implies that the variance of x bar is going to be smaller than the variance of x, right? So if I am going to, instead of just looking into x, if I add something to x and look into its variance, and by appropriately setting this weight, I actually ending up with a smaller variance, right? And that variance depends on this correlation. If my x and w are highly correlated, my variance can be very small, and in the case x and w are uncorrelated, so if an x and w are uncorrelated, my rho is going to be 0, right? In this case it is the same. I mean x bar and x will have the same variance. On the other hand, if there is some correlation, I am going to get a strict reduction in the variance. So this is the information we are going to exploit, and this is comes in under the assumption that there is an additional information that is available to me through this w. Okay, and that w has to be correlated with this. Whenever this happens, I can exploit this information and come up with a better variance. Now, okay, now the question you may be asking is when such an information will be available to me. Will it be available? Then I can use it, but where it will be available? Just think of some online delivery mechanisms and all, right? There you want to obviously to the users, you want to recommend a restaurant which is the best rated. Now you have so much of information, people are giving rating all the time, and you want to compute its empirical, you want to put some estimator on those ratings, but to get a better estimate, you can use some additional information. See, the people who are going to give rating, they will not just look the food quality, maybe they will also look into the delivery time. Like if that guy is not delivering, maybe you are not going to give him good rating. If he is good not only in food quality, delivery time, everything, maybe he will give good rating. So the rating he is going to deliver may also depend on delivery time. So somehow delivery time is going to influence his rating also, right? So what rating you gave and what delivery time, there could be some correlation. And as a platform, you know both of them, what is the rating they give and how much time it took to deliver the item. The platform can know this, right? I mean everything is displayed on your app. So maybe one can use this information to get a better estimate of the ratings. Okay? And to be more concrete, I have put this wireless application also. So nowadays, like we have these pico cells, right? I have shown multiple pico cells, and there are also macro cells. All these pico cells and macro cells, they will be connected through a maybe fiber backbone. Now this pico cell may be serving some mobiles, but all others, whatever it is transmitting that's useful information, everything else is an interference for it. But suppose there is a micro station here, it is also transmitting at some power, right. So, whatever that this base station can measure, what is the interference it is creating, because it is also seeing that interference, right. I mean, maybe not, it is not getting the same level of interference as this mobile, but it is seeing the interference from this, and maybe that interference information is good for this base station to see that which channel I should use, or on which channel I will get a better throughput or better error rates. So, the error rates or the throughput you are going to see on this mobile is somehow will be related to the interference that is being caused in the network. And so, if somehow this base station, Pico station can measure that interference, it can use that as an additional information to get a better throughput and better error rates for this mobile. So, that interference that it measures can be used as a control variate. Now, again I am putting all the things little formally here. We have k arms. In round T, I am going to, if you are going to play arm, I mean if it is arm, this is the actual reward xti and wti is its the additional information you are going to see, or what we are going to call it as control variate. And as usual, we are going to assume the classical, this sequence of rewards are IID, this sequence of control variates are also IID, but together they may be correlated. Okay? And now they have their own, each rewards have their own mean value variance, and we are interested in finding the one with the highest one. And control variates also similar thing, control variates have certain mean variance and the correlation coefficient is going to be rho I. Okay? In these things we only assume we know Wi, rest of the things we do not know. We somehow need to know the mean value of this control variates, but what is its mean value of the rewards, the variance, and what is the correlation between them, we do not need to know. Okay? And so, this is the interaction model. So, environment is going to generate the reward and the associated control variates, and the learner is going to select an arm based on the past observations of the control variates and the rewards. And what is the feedback? After he selects the arm, actually now the learner observes this reward value and the control variates. This is the difference compared to our classic. Earlier in the classical, this control variates was not there. Now this guy is also observing that. So control variate is the additional thing, but our reward regret definition is still the same. It is like what is the oracle would have given you and what is the total reward you would have gotten. And now the question is how to use your available control variate to get a better regret performance. Now to do this, we go back to the idea we discussed, how the control variates will help us reduce the variance. Okay? So now this is what we do. The estimates we are going to get, so this is our estimate based on our reward samples. To that we are adding the estimates of the control variate samples and we are combining them in a linear fashion as the control variate told us. And also we are going to choose this beta, which is now, if you look this carefully, the numerator is a, what does this sound like? This sounds like a correlation coefficient, right? And the denominator sounds like a variance. So, and we are, if you, the actual optimal beta dependent on the covariance divided by variance, but we do not know covariance and variance. So, we have replaced them by their corresponding sample empirical values. Okay. Now, unfortunately, things become suddenly complicated when you do this, because now you see that I am now interested in this new estimator, which is a linear combination of my original estimator and estimators coming from my control variate, but the thing that beta is now depends on my entire history. Now because of that, this guy depends on the entire, I mean it suddenly becomes correlated, like it's no more simply based on IID samples. So because of that, this Hofding's and Bernstein inequality, which requires that IID sampling, is no more applicable now. Yeah, I mean those of you have not used about Hofding, Bernstein, don't worry, but they need something which now gets violated. Because of that we can't use. But the good thing is, how many of you know central limit theorem? Okay, so central limit theorem is something like tells that asymptotically you are going to see something which is normal distributed, right? If you appropriately centralizing and normalizing. So that comes into rescue here. And how many of you know T distributions? T distribution? Student T distribution. Student T, yeah. So there is a connection between Gaussian distribution and student T distribution, right? And the connection happens through the central limit theorem. That could be leveraged, and for the Gaussian distribution, one can actually say that the new estimator we have, it still remains unbiased, and the variance of the new estimator we have, it is 1 minus rho I square times the variance of the original estimator we have. Now you see that the new estimator we have, it is already smaller by a factor 1 minus rho I square compared to the original, I mean variance of the original. So when we look into estimators, right, we look into two aspects, unbiasedness, and what's the second one? Its variance. Okay. Is an estimator just being unbiased is good enough? What should be the other property? It should have a smaller variance also. Okay, and that is what we are getting here. My new estimator is unbiased, but compared to the other variance, I am much smaller. And further, the deviation is also better controlled. I mean, you don't need to get into this, like it is the concentration inequality we have. Okay, the deviation of this new estimator, yeah, this mu hat C, right, compared to the original value, this is also going to fall very fast. So we are going to exploit this, and there are some terms here, right, VTS, these are like 1 by T to the power L quartile of the T distribution. And when we talk about T distribution, we need to talk about how many degrees of freedom it is. So these are all involved here. Okay, now once we have a confidence term whose variance we have better control over, then replace, simply go with that one. You replace the classical exploration bonus, right, with your new bonus. Okay, and then just use this as an index and try to find out the best one. And good thing about this, we know that this guy is already having a better smaller variance, and it will have a tighter confidence interval. So I will naturally anticipate it to do better. So this is a summary of the results we get. If we do this, if we go and do all the analysis, our UCB CV is going to give this kind of a regret bound, where lambda sigma, this is the maximum variance. We don't need to know it, but we will just, the regret depends on that. And this we are comparing with this classical methods, UCB1, UCBV, and extended UCBV. So you see that compared to all this, we are having this extra term 1 minus rho mean square, which you know is strictly less than 1. And that is because this is a correlation coefficient. So because of that additional information have, if you just compare these two, we have a significant reduction in by this much. And smaller the variance, sorry, larger is this rho square, we will get a smaller regret. Regret is going to be smaller. So this is what, like the gain, this is how one can incorporate any additional information we have. So use that information to get a better estimators, which will result in better confidence intervals, and use in your algorithm to improve the performance. Okay, I'll not go into that. Just one remark about this. This control variate theory comes with a rich analysis, and it is all actually linear regression. How many of you know linear regression? So if you look into this, that does not look like a regression problem. We need to identify what is the best B here. Just treat this as unknowns. You just go and do your regression fit, identify that best beta. The only thing we need to do is, we need to have construct some statistics over it and construct the confidence bound. And once all the things are Gaussian distribution, this linear regression will already, theory tells you what is, if you can treat these betas as unknown parameters and you can estimate, and it will also tell what is its variance. We are just using these properties of the linear regressions and using here. And that is what, like this is the nice thing, like using, you might be wondering why I just using this linear combination. We could have other combinations also, but linear regression is so well developed, we have many tools available right away to use here, and we actually use this. Okay, and all these things I said is for the special case of Gaussian distribution, but everything need not be Gaussian distribution. There are so many other distribution and arbitrary distributions, but for that also we can use our method, and I'm just putting the words here. Those who are interested can go back. So there are other statistical estimation methods called jackknifing, splitting, batching methods. This could be used, and we have actually used them to see how to adapt our method when Gaussian distribution is not there. I mean, these are some plots just to show that how the regret looks on some synthetic data. I mean, we have just compared with this classic UCB1, UCB Thomson, and what is that? Extended UCB variance. So empirically, if you just ignore additional information, right? Thomson sampling has been shown to do empirically better than all this UCB1, UCBV, and extended UCBV. But with our use of this additional information, UCBCV, we are always going to get best regret possible. And that we have shown it in, these are like different problem instances, and you see that all the time we will get a better regret bounds. Okay, so I will stop here, and this is some just extension we did. I just said there is a control variate, additional information available in every round, right? What if it's not available? Like why you think that I said rating and the delay, the time it takes. Sometimes maybe that all the time that information may not be available. In that case, if all the time that additional information is not available, how to take care of, that also can be analyzed in a similar way. But I think that brings in more mathematical complexities. We will not get into that. Okay, so in summary, we studied these multi-arm bandits with control variates, and these control variates are actually like additional information that is available in my learning setup. So we have this UCBCV, and when we have this control variates and Gaussian distribution, we are especially able to prove that we are getting a regret which is smaller by a factor of 1 minus rho square. And when Gaussian distribution is not there, there are other statistical methods available like jackknifing, splitting, and this could be used. Yeah, so one drawback of this method is, and which is actually the real drawback is, we need to know the mean of the control variates, right? That omega I said, that may not be always available. if that does not available, yeah, like one can estimate that also, but you need some slots or some samples for that, like to estimate how does that affect your performance. That need to be studied. We are studying that, but that's not complete. Yeah, I mean there could be other things like this can be used, like there are so many bandit variants, like I talked about some rotten bandit, cheap bandits, and dwelling bandits, right? In that also one can see that how if you have additional information in the form of control variates, how one can improve. So there is a big, I mean this whatever the techniques we have, this could be used in various bandit models and see how, I mean what kind of gains, like is it every time we kind of get this much gain, or depending on the scenario we can get more or less. Okay, so with that I will stop. Yeah, thank you. I think we overshoot some time. Okay, thank you very much. Thank you. Thank you very much. Thank you.
Thank you.